Mr. Mendez, what is a girder? Mr. Mendez, can you hear me?
Yeah,
What is a girder, Mr. Mendez?
Girder is
a strong or a small structural element.
Strong.
Strong. What's the name of the smaller structural element, Mr. Romero? Yandy Romero? Mr. Romero, what's the name of the smallest reinforcement element?
The small reinforcement is stiffener.
What's the name?
Stiffener.
Stiffener, yes, yes. Now, who supports the plate? Mr. Kimi, Andres Kimi. The plate, each plate, a panel, is supported by whom, Mr. Kimi? The plate supported by Mr. Gomez supports the plate. Mr. Gomez, who supports the plates?
The girder.
No, the girder. No, the girder. No, the stiffeners. The stiffeners are supported by the girders, and the girders are supported by the bulkheads. That's the order. Okay. Okay. So, and the simplest model that we said is that we could consider that each one of these plate panels would be clamped. But the problem is that we see that that's not correct, because the stiffener, even though, or the girder, even though it is very strong, it deflects a little bit. Once you deflect, that means that the support is not really clamped. So that generates a redistribution in the bending moment. And that's why more or less, we consider that the maximum bending moment and the minimum bending moment are about the same value, more or less. And we'll see that when we use finite element to analyze reinforced plate panels, okay? I can show you some of that in the next chapter too, okay? Now let's continue with our analysis, okay? Now, let's consider that, can you see my full screen? Andy, can you see my full screen?
Yeah, yes.
Okay, okay, now, let's suppose we have something like this, okay? So here we have a plate, okay? This is a plate, okay? Please look that it discontinues in both directions, okay? But more or less, we consider that from here to here is the spacing for these reinforcements, okay? Now, because of this external load, okay, this reinforcement behaves as it were a beam, okay? So you see immediately that the stress changes varies linearly, okay? And we have the largest stress in the bottom because we have the largest distance from the neutral axis, okay? But here, we recognize two effects, okay? Now, for the plate, I'm talking, okay? For this element, the plate, okay? This plate behaves developing a membrane effect, and also it develops some bending, okay? Now, if we consider that the plate is the flange, okay? We consider that the plate is the flange of the combination. Okay, with the combination, I mean reinforcement plus deck plate. Reinforcement plus deck plate. Okay, it develops normal stress. And we call it this membrane effect. Okay? So this stress, we assume that since the thickness is very small compared with this H, we assume that the distribution of the stress on the thickness is neglectable. So we consider that this effect, this stress is uniform. Okay? Since we put here, since it's much smaller than H, we assume that sigma is uniform on the thickness. So this is what we call the membrane effect. But there is also another effect, which is bending. Okay, so we see that the plate, okay, here, and about here, we have another reinforcement. But in between, the plate will do something like this, downward, and then will recuperate. So the plate is being bended. So locally, because of this, it will develop some normal stress. So it will develop, for example, it will go like this. Also, in the longitudinal direction, it will go like that. Okay? Okay, so this is what we call W. Okay? So the plate, deck plate, so bends. Okay? Developing stress in linearly in the thickness. And this is what we call the bending effect. Okay, so for example, let's suppose that this is the thickness of the plate. Okay, and here we have a bending moment. Remember, this bending moment could be mx or my. Okay, and remember, this is bending moment per unit length. So it has units of force only. Okay, but the thing is that here, the variation of this will be something like this. So on the top, in this case, will generate compression, and at the bottom, it will generate tension. Okay, so in this case, this sigma x will depend on Z. Okay, so this is what we call bending effect. And on the right-hand side, we have membrane effect, because the plate behaves as the flange of the combination. Okay, combination, I mean reinforcement plus deck plate or bottom plate or any plate. Okay, now let's see if we can do some deductions from it. Okay, so this is the plate. Okay, and this thing here is the membrane effect. Okay, and we say, this is what we're seeing here. We said in the previous slide that we assume that this is uniform because the thickness is so much smaller than the height stiffness. And here we have the bending effect. So if we combine, because the two effects are working together, on one side, you see that we have compression here. Let me see. This is in compression, or the whole thickness is in compression. Now, this part is in compression, but also this side, the top, because of the bending, is also in compression. So on the top, these two effects in this case will be combined and will give you a higher value in absolute value. And then we have a linear variation. And on the other side, we have a change in sign, in this case, since this is larger than that one, so we're going to have some tension. Okay, so in this case, the top of the plate, this is the bottom of the plate. Okay, and in general, we're going to have a combination of the two effects, membrane and bending. Now, if I know the stress at the top, okay, and I know the stress at the bottom, okay, if I subtract, okay, since at the bottom and at the top, we have the membrane effect. If I subtract, then I'm going to have a bending effect, okay? So if I subtract the, let me remind you, if this is X, this is going to be Z, okay? And this is equal to 6 minus 6 mx divided by t squared. So that's why here I have a negative here, because at the top I have minus, negative, and at the bottom I have positive. Okay, so if I at the top I have the stress, and also I have sigma. I have minus sigma x plus sigma, and then at the bottom I have sigma x, different sign because here I have minus t over 2, down here I have z equal to plus t over 2. That's why this is positive. Plus sigma membrane. So this one here cancels, and this is what I have. So elements, right? And you calculate the stress distribution. In that case, you're going to have a value of the normal stress at the top and another value of the normal stress at the bottom, right? So if you do this operation, and you can identify the bending stress, right? Similarly, if you add the two, you're going to have twice the membrane stress, right? So if you have in one case that, for example, at the top, the stress has one value, and at the bottom, you have similar value, but with different sign, that means that the bending effect is the most important. If in another case, if the value of the top and the value at the bottom are similar, that means that the bending effect is very small, right? So you can see that the plate is working mostly as flange or as a bending plate, okay? If we do this analysis, because in general, okay, the plate welded to the stiffeners will be providing both effects, okay? I don't know if there are any, Andy, is there any question about this, Andy? Andy, is there any questions about this?
No, doctor.
Okay. Now, I'm going to how this information from Timoshenko's can be employed in order to obtain the solution, in this case for a clamped case, okay? I'm going to do this example. You have this example yesterday, I posted in the Aula Virtual. So you have this in PDF version, okay? So we're going to compare a clamped plate, okay, with uniform load. Okay, so you have something like this, okay. This uniform load, and it's going to be clamped on all the edges, okay? This is X, this is Y, downwards Z, okay? So this is the information that we get from Timoshenko's, okay? And specifically, this is the plate that I'm going to consider, okay? It's a steel plate. You can recognize by the value of the Young modulus, okay? This is the Young modulus, newtons per meter square. In this case, A and B are going to be 1.5 and 0.75 meters. So this is 1.5, this is 0.75. The thickness is going to be 6 millimeters, okay, very small, this thickness, 0.5. So a few minutes ago, we recall the way to evaluate the plate bending rigidity. ETQ divided by 12, y minus no square. Okay, and more or less, this is the value that we can obtain. Okay, let's apply this pressure. Okay, this pressure is about what you would obtain in a ship which is resting, and the ship has a draft of 2 meters. Okay, so you would have here a calculator. You multiply 2 times 1,025. Okay, that's 2,050, and multiply by 9.8. We're gonna have this number. Okay, so it's like I'm trying to do something which makes some sense physically. Okay, now in this case we have to be very careful, people, because this is the notation that I'm using in class. Okay, I'm going to write it up here to avoid any confusion. So this is A, this is B. Be careful because this is Timoshenko's unit system. Okay, so the ratio A over B is 2. In this case, for Timoshenko, ratio is called B over A, but it's the same, it's 2. Okay, so I'm going to obtain these values, these formulas, to evaluate the maximum deflection, the bending moment here, and the bending moment at the center. And I'm going to compare those with the values that we obtained from application of the finite difference method, which is using the program by Engineer Ahila. Okay, now, if we have these values, 0.025, okay, 0.00254, Q, remember Q in this case is P0, is this value. A, remember that A is for us is B, 0.75, divided by D. D, we have this value, and this is what I obtained in millimeters, okay? If you want, you can later on, or you can do it now, you can check that this is the result that we obtain after applying this formula with these values, okay? Now here, I see an error here. I missed a negative sign here. Please correct in your class note. This is negative, okay? Because this is negative, okay, people? Now, here we have the formula, 0.0829, Q again, this is the pressure, and A is the minimum dimension of the plate, 0.75 squared. So I had a value of 935, okay? And if I take this value here, 0.0412, I obtain 466. And you can see immediately that this ratio, I can have 936 divided by 466. It's 2.0086. So more or less, that's the number that I was giving you, right? Usually it's about half, okay? And the center with respect to that value on the side, okay? So this is the application of the Timoshenko solution directly from this table. Now, Let's go on and try to obtain the solution, the same solution, using the program that it was mentioned before. Okay, so we have this. This is the data table or data file. This is data file. A and B, 6 millimeters in thickness. This is the Young modulus for the plate for the stiffness, and 0.3 is the Poisson ratio. In here, okay, in general, when we developed this program, what we were trying to do is we were applying a model that we call orthotropic plate theory, okay? Let's suppose that we have something like this, okay? And what we can do is we can transform this into a plate big plate, okay? So it's like making a combination of the plate plus the stiffness. So in this direction, since the stiffener is smaller, it's like having small material. In the other direction, you see that the girder is much larger. So it's like having more material in this direction. Okay? So we can see that the bending stiffeners, okay, is what we call dx and dy are different, okay? Now, in our case, we have no stiffeners. So what I did was, to avoid problems, I just put these values, these dimensions, very small, okay? For example, for the stiffener, I can have a web and a flange. Similarly, for the girder, I can have a web and a flange, okay? So you can see here that the web height, okay, the web height of the stiffeners in the x direction, this is the x direction, so the web height would be this dimension here. It's 0.1 millimeters. So this height here, it's really nothing. The thickness of this element, it's 0.01 millimeters. So basically it doesn't exist, okay? Similarly for the other dimensions, okay? So basically what we're analyzing is just the plate, okay? Because the plate has 6 millimeters in thickness, okay? That's the reason why I'm using these numbers, okay? Now, when you do this analysis, okay, you know that each one of the stiffeners and girders are welded to the plate, and you get part of this for the combination of the two. And that's the concept of effective plate, okay? In this case, since we are taking these values very, very, very small, that means that these two parameters make no sense. So you can put any value that you want here, okay? Similarly for these other two, okay? I have longitudinals in this direction and stiffeners in the other direction. And since they are basically nothing, you can put any numbers here. I'm just using one just because I need some number, okay? The rest of this is part of the rest of the data file, okay? Remember, these four numbers specify the support that you have on all the four edges of the plate, okay? So in this case, like this is X, this is Y, okay? So we have, this is the lower, this is the topper, right and left edge. And in all of this, I'm putting 1 because all are clamped. So you have to use the same values, okay? 1, 1, 1, 1, because in your case, it's the same as this one here. All edges are clamped. Now, here, I'm using these values, which is corresponds to the pressure, okay? What we did when we developed this program was we analyzed using a variable load. So we said we can use a value here, a different value here, a different value here, and a value here. And internally, the program, what it does is generates an interpolation. Like this. And after you break this into small pieces, it's going to interpolate linearly and apply the corresponding value on each one of the elements, okay? In this case, since we are applying a uniform load, the 4 values will be the same, okay? Then we go on and say this is 1, so we have 1 point load, but the values, you see that this is X, this is X, this is Y, and this is the value of the load. So this is 0, that means that we are not applying any force. And this is the number of points when you have a known displacement, okay? For example, you can analyze this plate and say, okay, I need this point to have a certain displacement, a known displacement. And in that case, the program will calculate for you the force that you need to apply in order to have this deflection. In this case, we have nothing of that, okay? So for your program, for your analysis, you need these 4 values equal to 0. In this case, 1, and in this case, X and Y are going to be the position where you have the force during the experiment, okay? So there's going to be, for example, 0.6 and 0.5, okay? And this here is going to be the force, the value of the force in newtons, okay? People, is there any problem about what I have said up to now? This is what you're going to be using for the report. So is there any questions about this, people? Please. Any questions? Is there any question? No questions. Okay.
Doctor, excuse me. This percentage in the left, 0.46 and 1, who represent or what represent?
Okay. Remember when we studied, I'm to write on this because I don't have more space. Okay. Remember that we have the concept of effective breadth of the plate, right? That means that if you have a plate like this, okay, you have a stiffener here. This is B, this is B, right? And we define it as an effective breadth. This here is BE over B. The problem is that you have stiffeners in both directions, right? So you have stiffeners in X and also in Y. And you could have different values for this effectiveness. So this is this ratio, the effectiveness ratio that we mentioned in chapter 2.
Okay, Doctor.
But in this case, since you are taking these elements very, very small, you see these values, this is the height. So this is 1 millimeter, so this is 0.1 millimeters. You can show with your fingers, 0.1, this is 1 millimeter. 0.1 is basically nothing. And you see the next value here, this is the thickness. And you see that the thickness is 0.0. So basically this is nothing. So basically in this problem, there are no stiffeners. So these values here and these values here, yeah, they are they are employed for the calculations, but basically they do nothing. They include nothing. Okay? The person who was asking me,
Okay.
would you please say your name?
Chin Chin.
I'm sorry?
Chin Chin.
Okay. Did I answer your concern, Chin Chin?
Yes, doctor, thank you.
No problem, no problem.
Doctor,
Okay.
good morning.
Yeah, go on.
I have a question.
Yeah, go on.
For a case in the report, where exactly we want to take our reference systems for this case?
No. See, remember that this program is already being applied. I mean, you cannot change that reference system. Okay. In this case, let me erase because I need more space. You can review the thesis from Engineer Ahila. But in general, you have something like this. This is X, this is Y, and here is your plate. In your case, you had I think one of the strain gauges were here, another were here, right? And you have two in the central, right? Okay, so the thing is, for example, let's suppose that we have a load here. What you need to specify is X of the load, Y of the load, and the force that you applied. What I suggest is take this value as the largest value that you applied, because in general, the problem is linear. Okay, so yeah, here you have the origin of the reference system is here in one corner. So the values that you see here, these two values, X and Y, these are this X and Y. Now, I'm going to say in a few seconds, okay, right now, this is the information that you provide to the program. Now, where are we going to have the results? I'm going to say that in a second, okay? I don't know if I answered the issue that somebody was asking me.
Yes, doctor, thank you.
No problem. Now, what's the next step? Everybody, don't tell me the contrary, everybody passed the numerical analysis class, right? Everybody. And now, in numerical analysis, what you do is you learn how to use the finite differences method. So you have the plate like this, and you say, for example, you can divide this. Let's suppose that we divide in 4. So we have 1, 2, 3, 4, 5 in the Y directions. And let's suppose that we have 2, 3, 4, and 5 in the X directions, okay? So in this case, NX is going to be 5, and XY is going to be 5, okay? So you're going to have the answer for each one of these points. And so on. Now, the problem is that you have, for example, the 4th derivative respect to X in the plate bending equation, right? So if you try to replace this in this point here, you are going to need 2 points to the right and 2 points to the left, okay? You use these 5 values of W to approximate the 4th derivative, right? So you need to include these values, okay, which are outside the domain when you work with clamped plates. That's why you will see in the results that you're going to have this plate is going to be presented a little bit displaced to the right and upward. Why? Because he's going to move the edge here to this point. Okay? And they're going to move the 0 from here to there. So it's like moving because he had to include these 2 rows, extra rows, in order to present the results from which are part of the solution, but which have no physical interpretation. They are outside the domain. Okay? Questions? Or please, questions? That's the meaning of these 2 values that you have to specify when you start running the program. Question. Okay. Let me show you. These are the results. Okay. In this case, I obtained this solution using, you can see here, the number of partitions that I employed. Okay. I employed 31 values in the X and 31 values in the Y direction. Okay. Here you have the origin. You see that in this direction, I have 1.5 and a little bit more because, as I said before, he's displaced in that direction. Because here, I have 2 extra rows because these are the rows that you need to include in order to evaluate the 4th derivative in that direction. Okay, remember that the largest value was 1.5. That was the 8th dimension. But in this case, since we include 2 more rows here, that's why we go up to 2. Well, not up to 2, just a little bit below 2. Similarly, in the Y direction. Okay, so this is 0.8, and you should go up to only 0.75. Why you need to include 2 more? Well, because, I'm sorry, this is, 0.8. That's because you have to include 2 extra rows here to consider to evaluate the 4th derivative in the Y direction. Okay. Now, in this figure shows you the deflection. Okay, I'm using a special program called EasyPlot. Okay, I'm going to write it here. It's very useful. Okay, if you want, you can talk to Andy or Marianiela. They can help you to try to explain how to use the program. And in the vertical direction, I have the deflection in each one of the points. So I have 31 values and 31 values. So that's a total of almost 1,000 values here. And you see that if you go in that direction, it starts slow and then start increasing dramatically. Remember that here, in this direction, the slope has to be 0. Similarly, for this case, you see that in this direction, that the slope has to be 0. So that's why these values here, this row, are very close to this one. But then you see the increment from here to there. So from here to here is very small, and from here to there is very large. Why? Because you need to go 0 slope, and then you start increasing to the top, and you go to the other side. Maximum value, this is 5 millimeters, I'm sorry, here. And this is below that, okay? In this case, using Timoshenko's result, we obtain basically 4 millimeters. So this is, I think it's very close to Timoshenko's result. Now, I'm plotting here, okay, MY at the side and at the center. Again, I need a negative sign here, okay? And the result, this is what they show me. This is MY in the vertical direction, and this is X, and this is Y, okay? So let me draw. So this is something like this. Okay, because you see that from here to here, I have 2 meters. This is A, and here it's 0.75. So this is the moment that I'm interested, okay? And the value here, you see that this is the largest value, it's about 900. It's Timoshenko gave me 436, and it is negative. Now, in the central part, you change sign, and you are below 500. Okay, so that means that we are very close with the result from Timoshenko. This is just an example to show you the way we can use this program in order to find this solution. Now, in your case, as I said before, you're going to include, you have to include you have to include, okay, these values, they have to be 0. And here, you have to include the position where the force is being applied, okay? Now, in your case, for example, the number of partitions that I employed is 31 by 31. So if you apply the program, what the program does is this, okay? So probably you are interested in this, for example. Let's suppose that I apply the force here, and I don't have a joint here. What the program does is he identifies the joint which is closest to the point of application of the force. So that moves you and applies the force in here. Okay? So, but if you have 31 by 31, I'm sure that the application of the point will be very close where the real application of the force it took place during the experiment. Okay? In my computer, I don't know what happened, but I gave him 31 by 31, and it took about some seconds. Okay, so you have to be patient. On the screen, you will see a message saying that the process is being developed. So be patient, and then you have the results. Okay. And of course, in your case, you have no uniform load. So these 4 values, they have to be 0. Of course, here, these values, the dimension AB and the thickness has to be changed by your adequate values. Okay, so you need to change these 3. These values have to be 0, and these have to include the position of the force and the value of the force according to the application of the force during the experiment. Any questions, people? Any questions? Any questions, people, so far?
Doctor,
Yeah.
it's not about this, it's about the assignment.
Mm-hmm.
I was working in the third, in the last problem, but for example, I define everything, but when I put in the conditions, the thickness of the plate and the iterations, for example, in my case, is working good when I apply, for example, 36 millimeters, and when M and N is 3, but and is working with all the conditions. But when I change that iterations to 5, it's a fail, and I want to get 1 more millimeter in the thickness, and I don't know how many iterations it's okay for our case.
What I would say is this, okay? 3 or 5 terms for the expansions are not very good. You need more. Why? Because remember that you are trying to simulate a concentrated force. So probably you need more. The easiest way to do this program would be, do not include the thickness in the controlling process. Run the program, you specify the thickness. Calculate the maximum bending moment, the maximum deflection, and from those two results, you can determine if you have to increase or decrease the thickness.
Yeah, I just did that because I only put at the beginning, and
Exactly.
only that, the number of thickness and the number of the iterations. But I just talking that
When you say iterations, what do you mean?
the values
Because
of M and N.
Oh, there are no iterations. Be careful. These are the terms of the expansions.
Well, terms of expansion. Yeah.
Yeah, the expansion. Yeah, but let me tell you something. Okay, 3 and 5 are too small because remember, this is a concentrated force. So I would say that you need more terms for the expansions. So, well, I cannot help you much with the Python. Probably you can talk to Andy or Maria Daniela Sayo. They have more experience in programming with Python. If you ask me for help using Fortran programming, yeah, I can do it, but not with Python. What I do when I have to solve these problems, see, I do not do it automatically. Then I run one and I get all these partial results on the screen. If they make sense, then, for example, in Fortran, there is an instruction which we call pause. So you run something, present something on the screen, and stop. When you hit return, he continues with the calculations. So I don't know if that's there is a Python instruction with something similar to that. Okay, so for example, you present partial results on the screen and stop. You see that these partial results are correct, hit return, and he continue with the next term. So you can compare and try to see where the error probably is. That's my only suggestion.
I did that, yeah, because I present the partial results, the max deflection, the max bending moment, and with that I compare and made a something that show me if that values are correct, that are available to continue with the program.
Mm-hmm.
Yeah, I did that, but that's my question. But if you tell that, but when I present or when I plot in the results, yeah, when I take MN small values, the graphic is not too exact. It's like a largest point in the position where we apply the load. But when I took more higher values, is have a better definition or better graphic of that. But until 10 is good because when I apply more,
but see, I don't see why it would make much of a difference. I mean, if you make include one term and include the next one, I don't see what's the reason why it shouldn't work. Because, see, one of the problems is that in some cases, you have a division by 0, right? In that case, yes, it blows up because it goes to infinity. But in these cases, okay, you have division by a number which is increasing in every iteration, in every term of the expansion. So if you increase the denominator, right, the result will be smaller and smaller every time. So I don't see why it should go up unless there is a problem in one of the instructions. But
yeah, it's just
right? If you increase M&N in the denominator, the quotient should be in every term of the expansion should be smaller and smaller.
Yeah, just until I just told that in just until 10, the value is increasing, but after that continues.
Yeah, but that's why what's what I don't understand. If the program runs correctly, for the 10th term, it should work correctly for the 11th, because the 11th will give you a smaller value.
Yeah, it's almost the same, 11, 12, and after that,
Exactly.
continue like the same.
Well, that means that there is, I mean, if I understand correctly, then what you can do is you can stop there, because there is no point in increasing more and more terms, because they are not giving you more extra information. They're so small that the next term will give you basically adding zeros. That's all.
Yeah, adding the same, yeah.
Yeah.
Okay.
Mr. Hidro, do you have any question?
Yes, it's about the last homework, and in the three problem about programming, it's say that we have to calculate the mean square error, but
Yeah.
that calculation is with mx and my. Yes.
Yeah.
When I did the calculation with Python, and everything works fine, except because I put that very low thickness because I made a mistake, but that's easy to solve. But the mean square error was high. I don't know, is the value have to be small or very high, because the number that the mean square error gives in Python is like 6,000 or something like that.
Yeah. Well, this is what I want, okay? For example, let's consider W, F, Y. Can you see my screen?
Yes.
Yes, doctor.
Okay. We have double summation, and we go from I equal to 1 to nx. And we go j equal to 1 to ny. Okay? Now, it will give you a certain result. And for example, in the center of the plate, so this is x, this is w, will give you something like this, for example. Now, we go and take the next one. So let's take, this is w sub nx and y. Now, in here, we include one more term. One more term only of this expansion. And we have a different result. I'm going to call just 2 prime, and here 1 prime. So this is there. If this is very, or is large enough, here you have something divided by m n to the second, and I think to the second. So that means that if this is, for example, 5 or 6, and you go to the next level, this term here will be very small. So the result for this would be very close to this one. So it will be something like, maybe like this. So you go and take some values here, 20, 30, whatever values you want, and you can evaluate the difference. But you can see that if this is large enough, and this is larger than those values, this difference is going to be very small. And in this case, the mean squared is going to be summation for each one of these terms, and you get W1 minus W, and then you square it. And they divide it by the number of terms that you take. And that's it. But what I'm saying is that if this is large enough, m and n are in the denominator. So this is raised to the 4th power. This is basically giving you nothing. So the difference between these two is going to be very, very, very small. So what I suggest is review this process to calculate the mean square.
I thought that we have to compare the mean square is compared with mx and my.
No. See, this is what we need. We're trying to approximate this function. And the problem is that this cannot be infinite because we don't have all the time. So this is what we need to compare, W.
Okay.
Okay, is there any other question, people? If you have any programming questions, talk to Andy or Maria Daniela Saya. They are more experienced than me in using Python for programming. Okay, is there no more questions? Then I'll see you Thursday with the program. If you have problems with the evaluation of the results or something like that, send me an email. I'm very interested in the results. Okay. If there are no more questions, then I'll see you Thursday. Okay. Bye now.